Hello everyone, you're welcome back to my channel. Today we are going to look at real and apparent depth. Actually, this topic is a continuation of refraction that I did previously. Okay, so when I talk about real and apparent depth, remember in that refraction we say that refraction is the bending of a light ray as it crosses the boundary between two media of different density, thereby causing a change in its direction. Okay, so we also explain it that when light travels from less dense medium to a dense medium, because the dense medium is denser than the less dense medium, it tends to do what? Bend away from the normal. The refracted ray tends to bend away from the normal. Is that okay? So today we're going to look at real and apparent depth. Okay, so let's explain what we have on the board. This is a basement. Okay, and we place, this is what we call rectangular glass block. This is a prism, a rectangular prism. This is a rectangular glass prism. Okay, so if we place this glass prism on a tracing paper, then we place it this way on a tracing paper, right? Okay, then we now put a pin, an object here at the edge, close to the tracing paper, on the tracing paper but at the edge. Now if you view from here to here, this is the real depth. From when you measure from here to this is the real depth of the object, because this is where the object was placed. But by the time you view from up, so you can see the object lying here, you're going to observe that the object appears shallower than it really is. Why is it so? Because light has traveled from one medium to another. That causes the bending at the boundary between that two media. Is that okay? And also, this glass is denser than air. What is the air? We breathe air. We look in through the air. Okay? Once the ray of light from your eye move from air, that is what you are seeing now is air, to another medium, it becomes refraction. Okay? It tends to bend at that boundary between two media. Okay, now this glass is denser than air. By the time you look through this glass to see that object lying horizontally here on the basement, on the tracing paper, you can't realize that the object will appear what? Shallow than it really is. It will not appear here. Is that okay? Because of the refraction that occurs between two media. Now if you measure from here to get the depth of the rectangular glass ball, if you measure from here to get where the object is lying, that is the real depth. Okay, then when you look through, this is what your eye, when you look through, you're going to see that the object has risen up to this point because of refraction. So by the time you measure from here to where the object is found, it becomes our apparent depth. And there's a relationship between real depth and apparent depth. It relates what? The refractive index. Okay, so we have that refractive index n is equals to real depth over what? Apparent depth. Real depth over apparent depth. Is that okay? Now we can also decide to find our lateral displacement, or we want to know how far in which this object was displaced. How can we do that? Knowing that the refractive index n is real depth from here to here divided by the apparent depth from here to here, we can actually get the lateral displacement, or the actual displacement in which this object has displaced. We're actually looking at the difference between the real depth and the what? Apparent depth. Is that okay? So that displacement L is equals to real depth minus apparent depth. So if you're able to get with this formula to get to real depth and apparent depth, you can actually get the lateral, the actual, or the upward displacement. Is that okay? I'm going to use this illustration to solve problem. So watch this video to the end so that you can understand how we can use the knowledge of real and apparent depth to find the refractive index, and also to calculate the upward or lateral displacement. Is that okay? Stay tuned. Let's look at this example. An object is placed directly below a glass block of thickness 3.0 centimeter. Calculate the lateral displacement of the object if the refractive index of glass is 1.5. So for us to solve this problem, what you are going to do is to set our parameters and know what you're actually looking for. Now this object, this is the thickness of the object, that is the real depth of the object, okay? So we are going to do it this way. We say real depth solution, real depth is equals to 3.0 centimeter. We're looking for lateral displacement, okay, that is our L, okay. Then we have refractive index to be 1.5, all right. But for us to get the lateral displacement, we must solve for apparent depth. So we are looking for apparent depth. So I'm going to use this formula. The refractive index is equals to real depth over apparent depth. My refractive index is given as 1.5. Is equals to, this is 3 over what? Apparent depth, sorry. Apparent depth, okay. Because I'm looking for this, we can say this over 1 cross multiply. Apparent depth is equals to 3 over 1.5, okay. So with the help of calculator, we divide. We say 3 divided by 1.5. The answer is going to give me, 2 centimeters. All right. Now for us to solve for lateral displacement L, remember it is real depth minus apparent depth. So let's subtract. Our real depth is given as 3.0 minus, and we got this apparent depth to be 2, certainly 0.0. When we subtract, we are going to have 1.0 what? Centimeters. So if you are given such problem, what you are going to do is to state the parameters, and for you to look for the lateral displacement, you must get the apparent depth. So the question is not a straightforward question, because you need to get the apparent depth using the formula refractive index n is equals to real depth over apparent depth, okay. Then making apparent depth the subject, we got 2 centimeters. All right, we now remember that lateral displacement is equals to real depth minus apparent depth, and we subtracted and got our answer as 1 centimeter. Hope you understand that. Let's look at another example. Let's check this out. A pool of water appears to be 1.0 meter deep when viewed vertically from above. If the refractive index of water is 1.33, what is the actual depth of the pool? There's something you must note. If they say when viewed from above, anytime you are viewing, you're looking through to see what is under, is your apparent depth. It's no longer your real what? Depth, okay. So this 1.0 happens to be my real depth. Anytime you're looking through to see what is under from above, it is said to be what? Apparent depth. So don't forget it. Let's set our parameters. We have solution. Our apparent depth given is given as 1.0 meters when viewed vertically from above. If the refractive index n is equals to 1.33, we're looking for the actual depth, which is what? The real depth, okay. So using our formula, n is equals to real depth over apparent depth. Now we substitute in to have 1.33 is equals to, you're looking for real depth over 1, okay. So what are we going to do? We're going to say this is over 1 cross what? Multiply. My real depth is equals to 1.00 what? Meters. Is that okay? So this is how we can solve the problem. This one, they gave us the apparent depth, because when you are viewing to see the object with your eye, it's said to be apparent depth. It's no longer the real depth of that, okay. So we set our parameters. We already have our apparent depth. We just substitute it into the formula, and we get our what? Our answer. I hope this video was helpful. If you are joining us for the first time, please don't forget to subscribe to this channel and turn on the notification button so that you get notified each time I post what? Videos. And also don't forget to comment and share this video so that other students and teachers can learn from this. I'm going to put up an assignment and you have to solve it and drop your answer in the comment section. See you next time in my next class. Bye.